display. This is your mind. From that, there is a theoretical deduction or an explanation. That explanation in quantum produces a cat in the quantum world. These are waves. What you're doing now is interpreting, according to quantum theory, you're interpreting the waves that come in here in terms of the classical world that you actually see. Okay? Dualism back again. Plato. This is what you see in the cave. This is what we now believe to be in the reality if we believe in quantum mechanics. Okay. Eric Reiter is going to talk about an experiment that he's done, which shows something, if we follow this, which shows something interesting. Here is the electromagnetic field. It hits a detector, and the detector produces little flashes, which you see. Now, the problem is that the wavelength is very large, about 1,000 times larger than the atoms. Right? So the people that did these first experiments, Einstein and his wife and so on, and the people at that point, they said, how can a huge wave, if it's an electromagnetic wave, be absorbed by a little tiny atom? You know, it's 1,000 times smaller. Right? And the answer was, it can't. It must be a particle. In order for that distributed energy to suddenly hit something that small, it must be originally a particle. So they projected photons into the world. Okay? We do this all the time. Scientists do it all the time. It needs to be straightened out. What's the result of that? They projected photons in here, and then they said, well, wait a minute. It doesn't always act like a particle. It sometimes acts like a wave. And it depends how I look at it. Okay, so again, they're saying, wow, here is something that I can't quite explain. I'm going to postulate something. I'm going to postulate the wave-particle duality. Nonsense. It's always been an electromagnetic wave. Well, that's also a projection. It's a better one. And the change takes place in the detector itself. That's where it turns out that one can, and nanotechnologies do it, but transistor radios have got these, they're called active resonant antennas. Very small antennas can grab energy from very large pieces, and that's actually what atoms probably are. So now Eric is going to show you something, and that may be an experiment to actually prove what I'm saying here. So I'm just going to skip this because the person I'm going to introduce
property of light, the collapse of the wave function. It's supposed to be where the wave goes both ways, but the particle somehow magically shows up in one detector, and it, in a way, is supposedly eliminates the click in the opposite direction. It's the collapse of the wave function idea. And we're going to look at this test very closely. People say a photon, they look at the model, they predict the model. All of the experiments that do this, they explain the experiment in terms of photons. But it's supposed to determine if the photon is there.
Right.
Acts like that. Next slide. Great. So this is the alternative that I have in mind. It's been examined since Planck, Sommerfeld, and Debye, but it's been given a bad rap in our textbook for several reasons. It's called the loading theory, the accumulation hypothesis. I call it the threshold model. It's like filling cups, where there's, in this case of light coming out, it's kinetic energy that's loaded up ahead of time, and that when a classical piece of light comes across, it will fill the top and make it emit a charge. But I'm going for a 2-for-1 effect. I'm saying it emits 1, h nu, energy, Planck's constant times frequency, and then it'll make 2 h nus, the same frequency. We're not dividing it in half. So, and that will show the distinction between quantum mechanical models and the loading theory, the threshold model. Next slide, please. So there are a few things we need to look at. There's a pulse height distribution histogram where we see that these are a nice narrow distribution of pulse heights, characteristic of the gamma ray that we're using, and we bracket it with our electronics to eliminate some noise, and so it's full height pulses. We're not looking at half pulses, in other words. Now, when everybody else does this experiment, they do with visible light, and the pulse height distribution is too wide. If you were to put the lower level here, you would count, the lower level too low would count half pulses, and that would not be fair to the loading theory. You put it up higher, it would remove many coincidences that would happen, and that would not be fair to the photon theory. No, it would favor photons.
What's the difference between the two theories?
That's whole questions, whole questions.
The difference is, well, I thought I said that earlier in the previous slide.
Just keep going.
Yeah. All right, next slide, please. Right. So we have to test if we're emitting one at a time to do this. And this is a standard test amongst nuclear physicists where you surround the isotope, you surround the isotope by 2 detectors, and you see if it goes one way, and then it makes a pulse, not a coincidence, then it goes to the other way. So we make this timing histogram where it could go click, click, we make a pulse, a number over to the left of the histogram, click, click, would be on the other side. If it's together, it would start to build up in the middle of this histogram. So if there was a source that created 2 at once, it would make a histogram with a bump in it. But we are using this one. We're using a radioisotope that does not create coincidences. It has a flat band showing that it's like noise. It's like looking at noise. You're really not seeing much detail there. Next slide, please. So this is the actual experiment. And lo and behold, we get a peak in the same histogram using the same electrons as before. Here we're going to rearrange the detector where it's one in front of the other. The isotope is over to the side. It's going through, and it's making coincident pulses. It should only be a flat band of chance coincidences, the way we saw it earlier, by quantum mechanics. We're violating quantum mechanics here by getting this peak in the histogram. Let's look at the numbers. There's the experimental rate that we read by the number in this peak over this time range. We do a background test and get a rate with the source removed, because there are some coincidences that happen from outer space. Then we correct it. Now we read the chance rate, which is standard amongst nuclear physicists where they do these kinds of tests. You get the rate in the first detector, the second detector, this time window, the same time window as before. Multiply it together, we get a chance rate. Then we take the rate of this chance rate the experimental rate to the chance rate, we see, well, we're 33 times chance in this. This is really great. It's a good one, particularly good. Let me see the next slide, please. Here's another one. So it keeps, this is another isotope. So it's a general case where I've been able to make this work many different ways. We get this nice big histogram. Over to the side of the histogram, you do see chance. That's nice. I get to see everything. The pulse height histograms of nice, well-behaved pulses. Works. Next slide, please. So when other people did this experiment, this is a famous version of this experiment. Very close to it. They do the same kind of histogram, timing histogram, and it's flat line. There's no hint of a bump in it the way I was showing, which means it's like chance. It went once to one detector or the other, only at the rate of chance, which is what quantum mechanics would predict. So everyone was happy when they saw this, and it was reproduced in several other ways and times. And until I see it the opposite way, because I knew how to look for it. Next slide, please. So yeah, I did this many ways, different isotopes, different detectors, I did do it where it looked like a beam splitter, and many self-critical tests. This is the name of the game, to try to prove myself wrong. So I've been doing this for 16 years. Next slide, please. If you look at the absorption spectrum of my detector, then over gamma ray energy, which is a photon concept, by the way, it really should be frequency, but I write it this way for convenience. So we're looking at, there are two different effects in the detector. There's a photoelectric curve, and there's a Compton effect curve. So these are the two isotopes, the gamma ray frequencies that I use. And you can see the photoelectric effect dominates, and that's what it's about. The photoelectric effect is the same. It's required for my unquantum effect to happen. When I defy chance, I call it the unquantum effect. And when I try up here in these higher frequency gamma rays, it doesn't work. That makes sense because it's about the photoelectric effect. Next slide, please. I split the atom the same way. The same electronics. Here's americium putting out an alpha ray, which is helium nuclear matter wave, otherwise known as the alpha particle. Usually it does act like a particle. It goes one way or the other way, but it makes this histogram defying chance a great big peak, which means it's split like a wave. It's not always like a particle. So how can it be? There's this graph here where it takes 7 MeV to split helium into 2 deuterons. But I only have 5.5 MeV. So right away, even if I was to look at 2 half-height pulses, next slide. So I looked at it closely. What are the relationships between pulse heights and how often it happens by chance? So here's one detector, pulse height to the right, the other detector vertically. And so most of the pulses are half-height pulses. And that gets 100 times chance. These are full height pulses. So I'm defying quantum mechanics in a few ways here by splitting it greater than the binding energy calculation and by defying chance for full height pulses. They're all well-behaved pulses. I look at every pulse on these experiments to see that they're good. Next slide, please. So this business of seeing the wave properties in atoms, that's been done many times. This is a particularly good version that other people have done. It shows that there's this wave where it can act like particle that goes through a diffraction grid, helium. Some will get focused. Well, how do you focus atoms? It has to go through many paths at once, which means it's not a particle. It really is a wave. I'm saying that there's no probability wave. The matter wave is a real wave. The light wave is a real wave. It's not a probability wave. I see it. I'm showing the distinction between the probability wave and waves we can understand. But there's no collapse of the wave function. It all works by the loading theory, by the threshold model. It's as if they're, it's like a soliton. A soliton can hold itself together, or it can lose it and spread like a wave. So that's the way matter works. Next slide, please. So this was the revelation when I was able to analyze these experiments famous for showing the wave properties. That here's there's an action to mass ratio in the de Broglie equation. So if you take the whole piece of wave that comes out, there's going to be action and mass and the whole thing. Let's look at a piece of the wave. Look, there's less in that cubic volume. I'm sorry, there's less matter and there's less action, but it's the ratio that's conserved. You can have a wave and not have it be a particle, but if you understand that it's the ratio conserved in all these equations, then you get to make sense out of it. It's that action is thresholded. Mass is thresholded. The charge constant is a maximum. They're all three of these constants are actually maximum, but we don't get to see less than the maximum. But we know it works that way by this equation, by this analysis, and by my experiments. I'm showing the distinction. Next slide, please. So with that idea and another way of seeing a factor of 2 correction using envelope functions, I was able to derive the photoelectric effect and the Compton effect and all these famous things without wave-particle duality, with something you can visualize. Next slide, please. This is what the experiment looks like. It's not that big a deal. There's a fancy oscilloscope. Here's the peak I was talking about of timing histogram. There's the thin detector in front of the thick detector, a nice nuclear instrumentation amplifiers. It's portable. I can bring it places to demonstrate. I'm hoping that I bring it into some lab here in UC Berkeley where they'll reproduce it. When it's reproduced, then we can say causality is restored. This is how I do it in my lab. There's this giant lead chamber. It works a little bit better that way.